Hello, measures of dispersion. Okay, it's not enough to know something about the middle of the data set. It's not enough to know something about the balance point of the data set. Take a look at these pictures here. And this is actually a figure from your textbook. If you look, going from top to bottom, we have these three bell-shaped curves. They're all centered at the same point, but their spread is different. Moving from top to bottom, the spread is increasing, but they have the same mean. So if we use the same mean, or if we use the mean to describe these three individual distributions, we might think that they're the same thing, but they're not. They're quite different. The dispersion between the three is very different, and so we want a way to reflect that. Okay, and so measures of dispersion, they convey information about the amount of variability in the data. Okay, a few measures that we're going to look at here. We're going to look at three of them. This first measure, called the range, it's a pretty crude measure, but it's used nonetheless. It's the maximum minus the minimum. Okay, pretty straightforward to compute. And is the range a resistant measure? That is, do outliers highly affect this thing? And that's the question we need to ask. And the answer would be to that question is the range is not a resistant measure. Outliers would highly affect the range. It's the max minus the min. It might solely be a function of two outliers. The range also is crude in the sense that it just uses two data points to say something about the dispersion of an entire data set. And so we're going to look for something a little bit better here, and that's what the variance and the standard deviation do for us. Okay, both of these quantities play off this idea of what's called a deviation. All right, the deviation of a data point is that data point minus the mean. So that's the deviation if we're dealing with the population, and this would be the deviation if we're dealing with a sample. And typically we're just dealing with a sample. But these are called deviations, and you can see if you have a positive deviation, that means that this xi is bigger than x bar, and if you have a negative deviation, xi is less than x bar. Okay, and so this gives us in some sense, at least for an individual data point, how far it is from the mean, and that's what we want to do here. So when we look at this first quantity here called the variance, it measures the variability by comparing each data value, that is each xi, to the mean. Okay, and we're going to first start off here with this is a sigma squared. This is the population variance. The population variance, you recall, because it's a quantity about the population, that it is a parameter. Okay, and so it's typically unknown. But when we look at excuse me, when we look at this quantity here, it's the sum of, we have xi minus mu, then we square that difference. So we're squaring the deviations. And so the point of that is, why not just, if I could just mark out that square there, why don't we just have that as our measure of variability? Let's just take this is in the sense the average deviation of the population. Well, if we do that, it turns out that some deviations are positive and some are negative. And when we add them together, they cancel each other out, and so the sum of the deviations is 0. So a way to get around this is to square each deviation and add that up and then divide by n. Capital N here again is this is the population size. Okay. Now in practice we typically do not know sigma squared, so we estimate it with s squared, which is called the sample variance. And I've got two representations here. Let's start off with this first one. It's the sum, I goes from 1 to n, of the square deviation from the sample. So it's xi minus x bar quantity squared. But then we divide by n minus 1. Again, little n is the sample size. The reason we divide by n minus 1 and not just n is there's a mathematical reason. It makes this s squared a particular kind of estimator for sigma squared, but we're not going to get into that for this class. Anyway, so this is our sample variance. Okay, this is an equivalent way to compute that sample variance. The sample size times the sum of the squared x's minus the sum of the x's quantity squared, then divided by n times n minus 1. Sometimes that's easier to work with, but we're gonna work an example through this representation here. So a question here: is the variance a resistant measure? And the answer to that would be no, because it's a function of the sample mean, and if you look at the sample mean, remember we talked about it not being a resistance measure. It is highly affected by outliers. So we have this quantity called the variance. It is, from the population variance perspective, the average squared deviation, and s squared, or the sample variance, is kind of like the average squared deviation, but we're dividing by n minus 1 instead of n. Okay, again, just to be clear here, little n is the sample size. Okay, what's often done with the variance is we take the square root of it. Okay, so we take sigma squared and we get sigma. We take s squared, take its square root, and we get s. And what that does is that allows us to measure the variability in original units. And what I mean by that is, suppose our data was the time it takes for somebody to walk to a particular location. And so that time could be measured in minutes. And when we go through this square deviation computation, that's going to square the minutes. And so our units are in squared minutes. But to have a dispersion measure, we'd like for it to be in the original units. And so we take the square root of our variance to get something in terms of the original units. Okay, and that's the standard deviation. The answer to this question is again no. The standard deviation is not a resistance measure. It's the square root of a measure that's not resistant, so it would not be a resistance measure as well. Alright, so let's look at an example of computing the variance, the standard deviation, and the range. And we're going to take the previous data set there that was from measures of central tendency, and I'm going to write the data and the necessary computations in a 3-column table. And this is a nice way to compute really a lot of summary statistics from a data set, in particular the mean and the variance here. So I'm going to have xi, and just looking back at the original data, 46, we had a 46, a 44, 43, a 38, a 45, a 42, a 45, a 44, a 46, a 44, and a 135. Okay, so I'm looking back at the original data. And if you recall, I'm going to treat this as a sample. So I'm going to look at the sample variance, here. The sample variance S squared is the sum of xi minus x bar squared. Okay, and I goes from 1 to n. That's the formula I'm going to work with. What I need is I need each deviation, and then I'm going to need to square them. But before I get the deviation, I've got to work with the sample mean. Well, fortunately, if you recall, actually I'm not going to put that there. If you recall, x bar was 52, and we worked that out earlier. So what I'm going to do is I'm going to have a column here that represents each deviation. So I'm going to have xi minus x bar. So first, what I'm going to do is the deviation for the number 46 is going to be 46 minus 52, and that's going to be negative 6. If I take 44 minus 52, I get negative 8. 43 minus 52, negative 9, and then so forth. This deviation is negative 14, negative 7, negative 10, negative 7, negative 8, negative 6, negative 8, and 83. So here's my deviations, okay? Now what I also need from the formula is I need to square each deviation. So I'm going to have a column for that. I'm going to have this third column here, xi minus x bar squared. So I'm going to square the first entry, or the first deviation there. So I'm going to take negative 6 and I square it. If I do that, I get 36. If I square negative 8, I get 64, 81, 196, 49, 100, 49, 64, 36, 64, and then here's a big one, 6,889. Okay, so what I like to do with this table is to consider kind of the bottom row here as the sum down each column. And so the sum for the first column, if you recall, we actually worked through that. That was 572. And when we took that and divided by 11, the number of data points, we got 52. Okay. Here, if we look at the sum of the deviations, you can verify this, but the sum of the deviations is 0. All right, add all these up, you get 0. It's kind of interesting when you look at all the data points, all the deviations are negative except this last one here. 135 is that extreme right outlier, and that has a large positive deviation, and all the other deviations have to add up to it, or in this case add up to it to equal that, so the sum of the deviations is 0. This should also tell us that we have an outlier when every deviation is negative except one. Okay. The square deviations, if you add all those values up in the third column, you get 7,628. And just looking at that number and thinking of the square deviation associated with 135, that data point is contributing heavily towards the sum of the square deviations. And so it turns out that this data point 135 is having a heavy effect on the variability measure. Okay, so S squared here is what we want to compute. I'm going to look at the sum of the square deviations. I've got that here. That's 7,628. Divide that by n minus 1. Again, n is 11. You know what? I think it's 11. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. 11 minus 1. So then I have 7,628 divided by 10. So that works out nice, 762.8. That is my variance, sample variance. And then the standard deviation would just be the square root of that. So if I take the square root of that, you'll want to punch that into your calculator. You get roughly 27.62. So this is my standard deviation. Okay, 27.62. That's the variance, the standard deviation, and the range. Here, let's compute the range. The range, again, is that crude measure, the max minus the min. So it's going to be 135 was the maximum value minus the minimum value, 38. Take that difference there, you have 97. So we've got our variance, our standard deviation, and now our range. And what we're going to look at in the next lesson is how can we use this standard deviation to tell us more about a data set. Okay, as it is now, the standard deviation from two different data sets compares the dispersion between the two different data sets. If we had another data set of 11 data points, or it doesn't have to just be 11, and we computed a standard deviation of, say, 12, then that would suggest the dispersion in that other data set is smaller than the dispersion in this data set. Okay, measures of dispersion.